Hi there, this is Coach Suiso, and welcome to Semester 2 of CAP Chemistry. We are going to start with chemical reactions as our first unit. I went ahead and decided to make my own videos for these first two lessons because I will not be here for these first two lessons this week since I'm still up in Michigan. I will, however, be back for lesson 3 before our quiz later next week, so you won't have any problem getting caught up. But I did want to make sure I taught these myself. If, however, you want to go back and watch the videos that are on the falconchem.weebly.com under chemical reactions, you can. They are taught by Ms. Warnow. So if you want to get a different perspective on how to do these, that would be a good resource for you. In the meantime, what you need to make sure you have out is your new pink packet for chemical reactions, because we're going to be using a packet now instead of with all of the lessons and all of the practices in one spot and all the labs in one spot, so you don't have to worry about trying to find different things, okay? All right, let's get started. This is chemical reactions. All right, there are 5 signs to look for in a chemical reaction. The first is that a gas is produced. The second is if a light is produced. The third is the formation of a precipitate. That is a key word that you want to make sure that you understand. A precipitate is a solid that is formed from 2 solutions. So you combine 2 solutions and then a solid is formed. It is not combining a solid and a liquid and getting a solid. It has to be 2 solutions, which are liquids, and it forms the solid, which is the precipitate. You could have a temperature change. If your temperature goes up, it is releasing heat, and therefore it is exothermic. If your temperature goes down, it is gaining heat, and therefore it is endothermic. Or some sort of permanent color change. All of those would be examples of chemical reactions. Another definition of a chemical reaction is the rearrangement of atoms to form new substances. Whenever you write a chemical reaction, your reactants are always going to appear on the left, and your products are always going to appear on the right. So if we're looking at this particular reaction in our example, we have 2 hydrogen atoms plus an oxygen, and it's going to yield 2 waters. So my reactants are these 2 on the left, my hydrogen and my oxygen, and my product is water vapor, which is going to be on the right. When we are writing these chemical reactions, we're going to have to balance them. The numbers that we're going to use to balance them are the big numbers. We call them coefficients, and they are the numbers in front of each of the pieces in your chemical reaction, either your reactants or your products. Your subscripts are the small numbers written in formulas. Those are these right here. Okay, this is a subscript. That means that there are 3 chlorine atoms in this iron 3 chloride. These are also subscripts, this 3 and this 2. That means there's 3 oxygen atoms in this nitrate, and there's 2 nitrates, okay? When you're balancing an equation, you cannot change these. You can only change your coefficients. And we're going to do more about balancing later on in this lesson in just a few slides. When you are writing your chemical reactions, there are several symbols that you're going to use. The first is S. That means you're working with a solid. If you see L, liquid, sometimes you'll see me write L as like this, a cursive L. Then G is a gas, and AQ is an aqueous solution. That basically means your substance is dissolved in water. So for example, if you see NaCl with AQ in tiny writing after it, in subscript form right here, that means that's salt water. It's basically NaCl dissolved in water. There are other indicators in vocabulary that mean you have an aqueous solution. It might not say aqueous solution straight out. It might say different things. It might just simply say a solution. It might say 1.0 molar. If you see that molar, that means moles per liter, which is basically, we haven't gotten into this yet, but it's essentially a way of determining how concentrated your solution is. So more concentrated or less concentrated. If you see sodium chloride is dissolved in water, that means it's aqueous. Or you could just simply see the word aqueous. So if you see any of these, all of these mean you would put AQ after it when you're writing that chemical reaction or chemical equation. Some other symbols that you're going to see in chemical reactions, most of these you probably know. You'll see a plus sign that separates your reactants or your products. So you read that as reacts with or and when you're reading them. You might also see an arrow, and that means yields. So that goes between your reactants and your products. You could see an arrow above your yield sign, which basically means you have added heat. Or you could see a catalyst, which is a substance above your arrow sign. And that's a substance that's used to increase the rate of the reaction. But it's important to note that it's not used in the reaction itself. It's simply making the reaction go faster. And then you might also see a double arrow. That means that your equation is in equilibrium, which is a later concept. We'll talk about it in the spring later. But it means that the forward and the reverse reaction are going to occur simultaneously. All right, let's throw it back to a concept that we talked about in August, and that is the law of conservation of mass. According to that law, matter is not created or destroyed in a chemical reaction. So the mass of all your reactants must equal the mass of all your products. You know that already. This is a review. So we did these questions. I've got example 1 and example 2 here. We actually did these questions on your matter and change exam, if you hopefully remember that. And there was also one on the fall final exam as well. So what is the total mass of reactants in the reaction below? So we're looking for that total mass. On the right-hand side, my products is 72 grams. The left-hand side, we don't know, but we know that you can't create or destroy mass. So the left-hand side must also be 72 grams of mass. Example 2 says, what is the mass of zinc produced in the reaction below? So on the left, we've got 40 grams of calcium and 125 grams of zinc carbonate. So together that is 125 plus 40. That is 165 grams of reactant. On the right-hand side, we've got 100 plus an unknown amount of zinc. Remember, these two have to add up to equal 165. So 165 minus 100 is going to be 65 grams of zinc. So now let's get into balancing. How do we actually apply this when we're balancing reactions? Because of the law of conservation of mass always holds in every single chemical reaction, every equation we have to be working with needs to be balanced. A balanced equation means that you've got the number of atoms on each element has to be the same on both sides of the arrow. So for example, if you've got 1 sodium on one side, you have to have 1 sodium on the other. Now, when you're doing balanced reactions, there's several ways of doing it. The way that I'm going to show you the way that is kind of traditionally taught, which is using sort of an atom inventory method. I prefer to simply use trial and error. That's just my style. So I'm going to do atom inventory for the first example, and then after that, I'm going to show you the way that I traditionally like to do it. If you prefer atom inventory, go for it. All the example problems that Ms. Warnow is going to do on the videos on the Falcon Chem will use atom inventory. There's no right or wrong way to do this, provided you get the right answer. The beauty of balancing reactions is you don't really have to show your work. So you can do whatever you need to do to show your work or use your work or chicken scratch to get the correct answer. And the other beauty of it is you can check your answer. You will know when you walk away from a balancing reaction problem if you got it wrong or if you got it right. There's no, I don't know if I got that one right. You'll know. You can check it. And if you check it and it's right, then you got it. If you check it and it's wrong, then you know you didn't. There's no gray area with balancing reactions, which makes it nice if you want to make sure you did it right. It's frustrating if you're not getting it, because you'll spend so much time checking it and realizing you got it wrong and kind of doubling back. So I'm hopefully going to teach you a way to make sure that you can do it every single time, teach you some kind of tips and tricks to make sure that you feel confident when you're doing these. But with anything in chemistry, but particular with this, practice makes perfect. Okay, so that's my little soapbox. If I was in class, I would have stood at the front of the classroom and given you that little lecture on that. So hopefully we do well on these, but let's give it a go. So an example of an equation that is not balanced is right here. I'm not going to highlight it because I don't want to confuse y'all, but let's just talk through it. I'll use a pen. So we got 1 sodium with reacting with 1 atom of iron 3 chloride, and it forms sodium chloride and iron. Okay, now let's check and see if it's balanced. We know it's not, but this is how we would check. On the left-hand side, we have 1 sodium. On the right-hand side, we have 1 sodium. For iron, on the left-hand side, we have 1 iron. On the right-hand side, we have 1 iron. For chlorine, on the left-hand side, I've got 3 chlorines. On the right-hand side, I've got 1 chlorine. So that immediately tells you that this chemical reaction is not balanced because I have a different number of chlorines. So what I need to go ahead and do is fix it so that it is balanced. But remember, the only thing I can change is this number in the front. I can put a number in front of all of these if I want, but I cannot, under any circumstances, change these numbers. Okay, there's a 1 here, there's 3 here, 1 here, 1, 1, 1. You cannot change your subscripts. You can only change your coefficients. So I need to change these chlorines. So I'm going to go ahead and put a 3 right here. Now that has given me 3 chlorines. Now my chlorines are balanced. But when I did that, in addition to giving me 3 chlorines, this now gives me 3 sodiums as well. So I have to come down here and make this 3. So now I need to fix my sodiums. I've got 3 sodiums on the right-hand side, but only 1 on the left. So I'm going to come ahead and put a 3 right here. Now, 3 and 3, 1 and 1, 3 and 3. My equation is balanced. And I'm done. Notice, I am not going through and doing this. I'm going to put it in blue. Do not do this. Put a 1 and a 1 right there. You do not need it. Like all things in chemistry and science, 1s are implied. So I'm going to go ahead and erase those because you don't want to do that. And there we go. We just balanced our first equation. All right, so let's do another one. Just as a reminder, I have at the top, only add coefficients, never alter your chemical formulas, which is what I just said on the last slide. Do not change your subscripts ever, ever, ever. All right, so let's do this one the way I kind of typically like to do it, which again, if you're an atom inventory person, you can do this. You can write your calcium, you can write oxygen, you can write carbon, and you can write the number of each one on each side. That is perfectly 100% fine. I like to just kind of start on the left-hand side and work my way across and do it with trial and error. So let's try it that way and see how you like it. And again, if you don't like it this way, you can keep doing the atom inventory where you write them all down underneath it. That is perfectly 100% fine. All right, on the left-hand side, I've got 1 calcium. On the right-hand side, I have 1 calcium. So far, so good. On the left, I've got 1 oxygen. On the right, I have 1 oxygen. Still good. Then I have 1 carbon here, but on the right, I have 2 carbons. Uh-oh. So there's my problem. So I'm going to fix it by putting 2 carbons right here. Now let's double check it. 1 calcium, 1 calcium, 1 oxygen, 1 oxygen, 2 carbons, 2 carbons. I am balanced. And that's it. So again, you could have done that with the atom inventory underneath it. It's completely 100% up to you. Whichever method makes this kind of puzzle make sense to you, that's the method that I would approach it with. All righty. Let's do this one. This one kind of has a bit of a trick to it. Not a trick, but like a tip for doing it better. That's a better way of putting it. So I've got, let's see, 2 hydrogens here. 2 hydrogens here, so we're good. Then I've got 2 hydrogens here, and then on this side, you notice I've got oxygen in 2 places. I have 1 here and 2 here. So that presents a bit of a problem because that means I've got 3 oxygens here. And it's really hard to get 3 in 2 separate spots to match up with an even number 2 over here on the left. So my trick for this one, and this is a trick you can apply whenever you need it. The trick for this one is double if you have an odds evens issue. So for example, here, I've got 1 here. I'm going to put a 2 in front of that. So I'm going to say double the H2O here. Now when I look at it, I've got 2 oxygens on this side, and I've got 1, 2 oxygens, 3, 4 oxygens. So I've got 4 oxygens on this side, and I've got 2 on this side. Now, because I did this trick of just doubling that, now it's easy for me to just double this in order to make it equal to each other. It just fixes my odds evens issue. So now I've got 4 oxygens on the left and 4 oxygens on the right. So if you ever have an odds even issues where you're like, I've got 3 on the side and I've got 2 on the, I can't figure it out, fix the odds evens issues by doubling the odd one, because then you've made it an even number and it might be easier to balance. All right, let's try another one. And I would, if you haven't already, take that trick. You'll notice on your notes page, there's a lot of open space on the right-hand side of your notes. I would write that trick next to that one. We're going to have a few tricks that are going to sort of help you out, just different ways of approaching problems. So when you're doing more problems later, this will help you practice. All right. This one, you notice in this one, we've got a lot of polyatomic ions. So the trick for this one, leave your polyatomic ions together. Do not split them up, because it's just going to make more work for you. Way more work. So for example, here, if I've got ammonium hydroxide, which is my first compound right here, I'm going to say ammoniums and hydroxides is what I'm going to look for on the other side. I'm not going to count nitrogens, hydrogens, oxygens, and hydrogens all separately, because you notice I've got hydrogens here and hydrogens here and hydrogens here and hydrogens here. It just becomes complicated. So the trick, leave your polyatomics together. So let's start from the left-hand side. I've got 1 ammonium, 1 ammonium. I've got 1 hydroxide. I've got 3 hydroxides, because that's little 3 right there. So I'm going to fix that by putting a 3 right there. Now, I just messed with my ammoniums, but let's come back to that and we'll check it at the end and see if it works itself out. Got 1 iron, 3 chlorines, 1 chlorine, so I need to put a 3 right here, and look, that also fixed my ammonium issue. So now let's double check it, because remember, like I said just a few minutes ago, you can always check and make sure that you got these right. You will never have to wonder if you got them right. So we've got 3 ammoniums, 3 hydroxides, 1 iron. Oh, sorry, let me go back to back. 3 ammoniums, 3 ammoniums, 3 hydroxides, 3 hydroxides, 1 iron, 3 chlorines, 3 chlorines. And we are balanced. All right, let's try another one. Okay. So this one is a combustion reaction, which we're going to learn how to identify in a later unit or later lesson in this unit. But there's a trick for this one. And so whenever you see combustion reactions, which look like this, you are always going to do them the same way. And the trick is leave an element alone for last. Okay? And then there's going to be a second trick, but we'll get to that in just a minute. Let me do that trick first, and then I'll kind of show you how it all plays out at the end. So leave the element alone for last. So you'll notice I've got this oxygen by itself. I'm going to leave that one for the end. And the reason you want to leave elements that are alone for the end is because you can alter them without messing with another element. So let's see. We've got, my little highlighter here. So we got 7 carbons, and here we've got 1 carbon. So I'm going to put a 7 right there. Then we've got 14 hydrogens, and we've got 2 hydrogens on this side. So I'm going to put a 7 right here. So now my carbons and my hydrogens are completely balanced. But my oxygens are not. I've got 2 oxygens here, and then over here I've got 7 times 2, I've got 14. I'm just going to do some chicken scratch there, and then I've got 7 over here. So in total, I've got 21 oxygens on this side. And my problem, I've got a kind of an odds even problem here, right? Because I've got 2 oxygens on this side and 21 oxygens on this side. But the beauty of this is I can do this without messing with any other element. So I need to get this side to equal 21 oxygens. So start by just doing it straight. Don't overthink it. What times 2 equals 21? Well, it's 10.5. Now, technically, that's balanced. I'm going to erase all my chicken scratch. That is technically balanced. I have the same number of every element on both the left and the right. However, can I leave 10.5 oxygens in my equation? Hopefully you kind of went, no, I know I can't, because you can't have 10.5 of anything. But we learned when we did empirical molecular formula, if you've got a 0.5 of something, how do you get rid of it? Well, you multiply it all by 2. So I'm going to go through, multiply this by 2. I'm going to multiply this by 2. I'm going to multiply this by 2. And I'm going to multiply that by 2. And now my equation is balanced. 2, 21, 14, and 14. So the end of my trick there, it's leave an element alone for last and then double if you need to. And the nice thing is you're going to do that same trick I just did right there with the oxygens on almost every single combustion reaction. So if you ever see a combustion reaction, which we're going to learn to recognize in a later unit where you've got an oxygen by itself, you're going to have a hydrocarbon, an oxygen, and always carbon dioxide and water. If you ever see that oxygen by itself, you'll typically do it like this. All right, that concludes lesson 1 on reactions. You're going to go ahead and work on the practice, which is in your pink packet. I've left the sub instructions on which pages you're supposed to work today. Remember, practice makes perfect on balancing reactions. So you're just going to work on practice, 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 and make sure that you feel really confident with it before we go on to the next piece of this unit. All right, good luck.